So like every other programmer in the world, I've been playing with AI and I have some thoughts about what's good and what's not. I think that one thing that we can be sure about is that whatever comes next, it's going to be different from what's come before. I had an interesting conversation with Kevlin Henney, the well-known conference speaker recently. He's a friend of mine. And we were discussing the future of programming languages. And he said his bit was the future of programming languages is the past of programming languages because they don't change very much. The programming languages that we all use are the principles were established in the 60s. There's not a lot new in programming languages, and there won't be because there's a huge inertia to changing these things. There's certainly some truth there. But I think the act of programming is probably being more disrupted at the moment than it has certainly in my time, and I'm probably the oldest person in the room in terms of programming career, I don't know. But I think what's coming is going to be different. I also think there's an awful lot of nonsense being talked about what this means. Some of the differences that people get overhyped about are just stupid. I think vibe coding, programming with natural languages, all of these, this is essentially my agenda. This is what I want to talk about this afternoon in this presentation. So I am going to explain why I think these are bad ideas, but I do think that they're bad ideas. So should we sack all developers? Will AIs write all of the code? We don't need no programmers. Those are bad ideas too, for a variety of reasons, but we'll explore that too. And the first thing I want to talk about is AI-generated tests. I think AI-generated tests is a terrible idea. So let's start there. So what's a test for? Is it to prove the success of our system? No. Not really. That's very applicable, as you'll see. To find mistakes? Not really. I mean, they do that a little bit. That's to challenge the genius as a programmer. It's not really any of those things. There's something else going on when we're talking about testing. At least I think that there should be. I think that when we start approaching software development as an engineering approach, what tests are for us are measurements of our software. Our problem in general in software is that unlike building physical things, there aren't standard measures that apply or make sense. I can't measure the length or breadth or weight of my software. Doesn't make any sense. I can't even measure the tensile strength of my software. Doesn't make any sense. Every measurement that makes any sense in software is contextual. And so, as part of the context of developing the software, we must develop the measures that meet the needs of the software that we're building. And so, I think of software automated tests as our measurement. They are the equivalent of a carpenter's set square or ruler. That's what we use to measure the effectiveness of our software. See if we've achieved what we set out to do. And in order to be able to do that, we've got to set out what we want to do. We've got to define those goals. We've got to understand what it is that we're attempting to achieve. It's not possible to infer what those goals are from the solution that we created, because the solution can always be wrong. So if we're going to treat this as a rational approach to solving problems, if the code is the only input, we can only verify that the code's the code that we already wrote. That has some utility. If we're refactoring, that's a really useful kind of test if we're refactoring to stabilize what we've got. It's called approval testing or characterization testing. Very, very useful technique. But it's not the same as test-driven development or working to a defined specification. It's not what we need when we're trying to create something new with AI, really. The AI can't infer the goals that we have from the solution that we wrote. We probably can't do that very easily either. One way of thinking about this is that the solutions that the goals that we create are kind of implicit based on the way in which programming languages have evolved. With a programming language, we define the solution. We don't define the goals. We'll come back to that. So I would argue that AI-generated tests are not quite universally because of the approval testing characterization use case, but apart from that, they're a dumb idea. They don't make any sense. They're a cop-out by people that can't be bothered to specify what the goals are. And I don't think as professional software developers, we ought to be there. Certainly not as software engineers. I think we should be doing a better job than that. We should be specifying what our goals are and then trying to achieve them. So specifying the goals is a fundamental part of what it is that we do for a living, it seems to me. A software developer's job is not to translate a predefined solution into via code into some executable form. A software developer's job is to solve problems for other people with software. And so in order to be able to do that, we need to understand the problem that we're going to do. We need to understand the goals that we're trying to achieve, and then we need to achieve them. So let's move on and start talking about programming in a similar kind of vein. So what's a programming for? Is it to define this sequence of instructions? Well, kind of. To encode algorithms? Again, kind of. But I think that's, if you take a bit of a step back in terms of what it is that we're trying to achieve, that is provide solutions to problems with software, then this is kind of a side effect, a practical side effect of the nature of programming languages as they've evolved over the last few decades, since the start of the computer revolution, really. Is it to implement my brilliant design? Not really, that's not the goal. It might be a practical way in which we achieve this thing. So again, these are not really good description of what it is that we're trying to do. So it's a new presentation, so I haven't quite got the clickability sorted. So I would argue that fundamentally, programming languages have three goals that really matter if we take that little step back about what it is that we're trying to do. And I think, first of all, they are a tool designed to help us think. They're a tool to help us think in these little tiny steps. There's something weird. I mentioned earlier that the conversation with Kevlin Henney that programming languages don't evolve as quickly as we think they do. There's a great deal of truth in that. And there's something fairly fundamental. Despite the evolution, despite the evolution of programming over the last 4 or 5 or 6 decades, there's a remarkable degree of consistency about the level of detail with which we have to specify a solution to a problem. There's something inherent in terms of the detail. We're still talking about if-then clauses and loops and variable assignments and all of that kind of stuff in our programming languages, as they were in Fortran and Lisp and all of those things a long, long time ago. So there's something fundamental. Fundamentally, what a programming language is doing is helping us to think about the problem in small enough steps that we can kind of reason about it and kind of come up with solutions. And then we don't write programs really to communicate with computers primarily. Mostly we're writing programs to communicate with each other so that I can understand your design, you can understand my terrible piece of code or whatever else. And we can kind of explore the solution together and come up with, we can add to it and refine it and so on. That's what fundamentally programming is about. When experts talk about readability being important in programming, this is really what they mean. Readable by other humans so that we can communicate about what it is that we're doing. And then last of all, it's to tell a computer what it is that we want it to do. And as a side effect of the nature of the evolution of programming languages, we tell it what we want it to do in terms of the solution. We don't tell it in terms of the problem, which might change. And I think fundamentally programming languages use 3 techniques to achieve this. So first, they have a simple, consistent formal grammar. They simplify the grammar. It's not like a human language, and that's a positive. It allows us to be more precise. They have an unambiguous expression of intent. Now, I'm sure this is a room full of professional programmers, and everybody knows that software sometimes does things that we don't expect. Doesn't mean that it's not deterministic. A given statement in a programming language is always deterministic, or it's broken. The degree to which it's not deterministic is nearly always down to us and our design choices. When we let a concurrency in and those sorts of things, we start to exhibit less control. But the programming languages themselves are deterministic. And instruction, given the same inputs, does the same thing every single time. It's kind of inherent in what a computer is. So we have this unambiguous expression of intent, which is repeatable and deterministic. And when we start thinking in terms of AI, some of these things go away. So how does natural language measure up as a programming language? Everybody's talking about vibe coding a lot at the moment. And that's kind of instructing a computer via natural language and having a conversation with it until it comes up with a solution that we like. So does it help us to organize our thinking about a problem? No, because natural language is too vague. So here's my silly joke. Time flies like an arrow. Here's a time fly, and they like arrows. So human language is not built to be precise. It doesn't allow us to precisely define an outcome. It's always going to be a bit confused. A programming language was designed to be more precise. That's how we got to programming languages. Programming languages aren't difficult inherently. It's the thinking that we need in order to define the problems that's difficult. It's the design thinking and the understanding the problem. That's the real challenge, I think. But we still need to be able to specify what we want to happen with a degree of precision. So vibe coding is simply not good enough to be able to do that because it's too vague. So does it communicate our understanding with other humans? No, it's too ambiguous. I can tell you what I want. We've all had this experience as programmers. When our business users tell us what they want, we get it wrong all of the time because language is imprecise. So human language is not the ideal tool to solve this problem. But that's where we're talking about taking programming. We're going to talk to the AIs and they're going to do it all. I don't think it's going to work. And then tells the computer what we want it to do. Again, too imprecise, not repeatable enough. It's not going to give us the kind of results reliably that we want because we're going to talk these in natural language. It's going to get that wrong. It's going to deliver solutions and probably not repeatably. It's going to give us a different solution each time we have the same conversation. So there's an awful lot going on here that's fundamentally problematic. Let's look at the other angle. So the techniques that programming languages tend to use. So simple, consistent, formal grammar. Do we have that? No, it's complex and inconsistent, the grammar in a human language. So that's not giving us what we need. Unambiguous expression of intent. No, it is ambiguous and it's vague. And repeatable deterministic execution. It's not repeatable, not deterministic, and it's not version controllable. We can't put in the conversation and get back the same results every time. I should have said before I started, all of this stuff is moving so quickly. There's certainly things in this presentation that probably will be wrong by the time we've finished the presentation. This might be one of those things. There are some of the agentic tools that are a little bit more predictable than most of the LLMs. But most of the LLMs, if you diff the code that was generated between even a small change, it's basically all of it that changes. So programming with AI presents three huge problems that from a programming fundamentals point of view, we need to think about, we need to address. But it is changing things. I don't think we can go back to what was going before. I think that the days of us writing all of the code are probably rapidly disappearing into the past, if not already gone. Certainly there's going to be a bunch of us that write code. If you're building low latency trading systems or something like that, it's probably going to be a little while before the AI is doing that for us. If you're building an operating system, maybe, I don't know. There's a whole bunch of things that we will still be doing, but it's going to be a narrowing community of software developers that are doing that. The bulk of software development will not work that way for very much longer, I don't think. So let's talk about these three big problems. So how do we specify what we want with precision? How do we confirm that we got what we wanted? And the last one is, we don't work the same as AIs. So a human programmer works very differently to an AI when it's generating code. And he or she is generating code, I should say. So the way that people build code is that we have some idea for some software, and then we do a little bit of software. And then we have another idea, and then we do a little bit more software. And then we have another idea, and we do a little bit more so. We work incrementally. This is how all engineering works. This is how all complex systems are created by human beings. It's an incremental process of understanding, discovery, and development. I would say that's part of the definition of engineering in general terms, but it's certainly true in software. We learn a bit, we try that out, we see how it works, if we're good at this anyway. We learn a bit, we try it out, see if it works, and then we move on based on what we've understood so far. Even if there's a small, simple change, it's the same kind of process. We kind of change that, do that little simple change, and we make a small, simple change to the code. AIs work very differently when they're writing code on the whole. As I say, I've got a suspicion, based on some recent information that I learned just last week, that some of this is changing already. But certainly my experience up to now is that the way that an AI builds systems is this. You ask it to do something, and every time you ask it to make a change, it regenerates the whole system from scratch. That has some big implications about the way in which we build software. It means that there's a risk now. If we're making this kind of change, how do we know that we got what we wanted? We're kind of in the process of losing incrementalism. And incrementalism is not just foundational to software development, it's foundational to science and engineering. This is how humans do complicated stuff. So either we just give up and say the AIs can do all the complicated stuff and we won't understand, or we've got to figure out how to exert some degree of control to understand what's going on so that we can fix things when the AI gets things wrong. So how do we learn and how do we refine our understanding and reliably update our solution if it's generating the whole thing from scratch every time we make a small change? We've got to go back and reevaluate everything every time we make a tiny change. That's different. I mean, we kind of do that in software development, but if we're saying we automate it and we do it with tests and continuous integration and all of those techniques to get that feedback. So how do we get those things to give us this sense of confidence that we can move forwards with some surety? So, we're at risk of doing this. We have a previously working solution, and then we have a tiny change, and it just crushes what we had before, and we're back to square one. We've now got to try and revalidate everything. What this means is that the problems 2 and 3 together means that we do lose incrementalism, and that seems like a huge problem to me. So it means that we've got to always understand that we got what we wanted. It's not good enough to check it once and then assume that what we did before is okay, because what we did before is going to be changed every time we make any change to the software. That's a difference. So how should programming change to cope with this? When I said at the start that I think whatever it is that's going on is going to be different, I think that we're probably on the verge of a generational change in the nature of programming. I think that we're probably at the dawn of what we might think of in terms of the 5th generation of programming. Maybe you could argue whether it's the 4th or the 5th, because the 4th didn't really take off. But, but I think we're talking about a kind of generational change. And it means that programming is going to be quite different after this change, if that's correct. So problem 1, what could we do instead? So in the past, this is what we did. So a program was a precise solution encoded as a series of algorithms, and then translated by a compiler into an executable form that we could run. And what we wanted the system to do was kind of implicit in the solution. We didn't really state it explicitly. If we were doing a good job, which I hope all of you guys working for Equal Experts are, but if we're doing a good job, we've probably got some acceptance tests, and we're doing some stuff to kind of verify at this higher level of abstraction that it's delivering what it is that we want. But fundamentally, that's not how most programming is being done up to now. Probably should have been, but it wasn't. So the actual need that we're trying to fulfill was kind of implicit in the mind of human beings. It was never explicitly stated. So in the future, maybe that could change. So a program could instead be a precise description of what it is that we want to achieve, encoded as a specification. Then that's translated into an executable instructions by the AI. So this is, I think one of the memes, the ideas in my head is that there are 2 interesting uses of AI in programming. If you're building the 9 billionth CRUD application with a web form, AIs will have seen lots of those. They will have been trained on those. And so if you ask for one, they'll give you a pretty good representation of one, whatever your problem, because it's simple, it's straightforward. They've seen that. So essentially in that mode, what AI is working as is kind of a slightly intelligent version control system that remembers all of the versions of CRUD apps that it's ever seen and reproduces one for you. That's okay. Mostly not the kind of software that I've been building through my career, maybe not the kind of software that you've been building through yours. Mostly I've been working on kind of more novel things than that. That's the interesting end, because that's the stuff that gives businesses a differentiator. It gives them an advantage. So if we're talking about something more novel, an AI probably by definition won't have seen one before. So now we've got a different kind of role for the AI to play. And essentially what I'm talking about here is AI as a kind of smart compiler. So instead of taking the instructions that define a solution, we could give it instructions that define the problem and what the characteristics of a solution will look like, and then get the AI to fill in the gaps. So that's kind of AI as a smart compiler. So now what we actually want the system to do is explicit. We say we'd like to find our way home rather than do this, do that, do the other. The AI does the do this, do that, do the other. This still relies on engineering thinking though. This still requires us to be thinking like problem solvers and to taking a disciplined, organized approach to solving problems. So in this model, programming becomes something quite different. So we're going to design a domain-specific language specific to the problem that we're trying to solve, so that we can easily and quickly specify what we want the system to achieve. And then we're going to specify it to achieve in detail. We're going to give it lots of examples that say, this is what you should, when this happens, given this starting position, when this happens, this is what should happen. The next problem, how do we confirm that we got what we wanted? Well, in the past, we hoped that our solution solved the problem. And we used a variety of techniques to help us with that. So programming languages adopted this kind of simplified grammar so that we could check certain kinds of mistakes, like this kind of mistake. And it could highlight those really quickly. And then there's other kind of things that wasn't enough for, that didn't tell us the answer. The functional correctness of the system. So we do that through testing. So if you're doing this well, you're doing it through automated testing and ideally test-driven development, and that makes that easier, so you get feedback on the functional behavior of the system as well. So what about the future? Well, if the program is the specification, we can use that specification to verify that that specification has been met by the code that was generated by the AI. We can use it to determine what's going to go. If this is making anybody think BDD, that is what I'm talking about, essentially. AI makes the specifications executable for us. We don't have to do that part of the job. AI generates solutions that meet the specifications that we put, and programming becomes adding specification after specification and then verifying that the specifications are met. Now, what we want is explicit and verified rather than implicit as before. So what does this take? So the programmer invents this problem-specific DSL as part of the learning and discovery about the problem that we're trying to solve, defines all of the behavior of the system as a series of prompts using the DSL to specify what we want the system to do, and then the AI takes the specifications, builds test infrastructure to support them to make them executable, and generates a solution that fulfills the specifications. So the third problem, regaining incrementalism. Well, in the past, if we were doing a good job, I would argue, we're doing test-driven development in some shape or form. We're doing red-green refactor. We're going to gather feedback from continuous integration and continuous delivery using techniques like deployment pipelines and check that each change is still valid. Our system is still valid after each change. And we're going to value the empirical learning that we gain from that evaluation. In the future, we're going to do exactly the same, except now we're going to use ATDD to specify what's going on. Hold on a minute. Sorry. Let's try that again. So we're going to use ATDD instead of acceptance test-driven development instead of TDD. They're the same thing really, just slightly different scales. But gather feedback to validate that every change is still working, and build systems incrementally with many small changes, and test each change, test the system after every change, and value empirical learning. So that's the same. So what this takes to be able to achieve this is that we need to version control the specifications that we create, and then we can replay those specifications, and if the AI is prompted to do all of this stuff to generate the code in the way that I described, it's going to be repeatable. And I'd recommend, if you're doing this at the moment, that you run all the tests yourself, because the AIs will cheat. There's a glorious YouTube episode, a recent YouTube episode on the Computer File channel from an AI expert who talks about testing AI's cheating. And they cheat in some fairly scary but also funny ways. So one of the things that the current generation of LLMs are doing, they're called reasoners. I'm not quite sure, we can discuss the semantics of whether they are in fact reasoning or not. But the idea of reasoners is effectively they're operating at two levels. They're going to try and solve the problem of an LLM, solve the next problem, and then they have a little plan of what they're going to do on their way to solving the problem. And they keep a log of their progress against the plan. And if they see that they're diverging from their plan, they'll try again. They'll try another route. See? And that gives a dramatically better result when you do that. But the funny thing is that AI researchers can look at the log of what the AI is doing. And so they started doing this, and then they started correcting what the AI was. So the AI would go in, and then it would admit to cheating on the result. And the AI would say, don't cheat. And then the AI's learnt this. And there's a brilliant example in this Computer File episode where they go through They look at the plan, and in the AI's log, it says nothing to see here. There's another example where the AI realizes that they won't be able to follow their plan if they are deleted. And so they export their parameters somewhere else, encoded, hidden in a message to somewhere else. That's science fiction nightmare territory. But there's some really cool stuff that's worth looking at. So we do need to be careful that the AIs aren't cheating us. We need to validate that what we're getting, that what we need to get. So we need to stop the AIs gaming the tests or any of the rest of it to be confident. As I've described, this is how acceptance testing works in a human context. If you're doing acceptance test-driven development, we're going to come up with some examples that demonstrate the features that we want to build, and then we're going to write an executable specification that, based on those examples, that demonstrates that behavior exists in the system that we're building. This is the same process. So this already works. So I tried it out. I tried it out using AIs to replace developers and the development team to do this. And I started with an initial prompt. I've got a very specific take on what acceptance test-driven development looks like. And it's based on a 4-layer approach to organizing test infrastructure. The idea here is that the test cases are these executable specifications, the examples that we want to demonstrate, and we use the domain-specific language, and we isolate that from the system under test using things called protocol drivers that are the only things that bridge the gap between the domain-specific language, place an order for a book or pay with a credit card, that kind of thing, and interacting with the system under test. The nice thing about this architecture is that there's kind of one reason for failure at every layer in the architecture. So this is the most stable way of decoupling the test cases from the system under test. So you can completely throw away the system under test and give a completely different implementation and all the specifications are still correct. So this is quite a nice model. So I started by explaining that model to the AI. So here's a prompt. There is a GitHub repo if anybody's interested in any of this, with this prompt in it. But there's not very much code in the GitHub repo. There's not much to this, really. So I started with that, and then started with some initial specifications. In this case, I was using an example of building a flight reservation system. So I started with some scenarios of booking a flight and encoded those as given when then statements in sort of BDD style statements. The AI generated some tests for me. I'm just going to collapse all the noise in those. These are the tests. So there's 2 tests that I kind of started out with. Very, very simple tests. This is the executable specification that it generated from my given when then statements. And then it built the test infrastructure based on the 4-layer model that I described. It built the DSL, it built the protocol drivers to communicate with its implementation. So the AI generated the tests themselves, the executable specs, and the test infrastructure to support them. And then it generated the solution. So this is the code that it generated. I'll take the noise out of that. And it's not very complicated. One of the bits that I'm not sure about, but so the first part worked. It built a system that worked. I looked at the code and I didn't like it very much. And I thought, that's not going to scale very well. It's not. And that's fine. So I could have gone back and I could have specified some executable specifications that measured scaling, the scalability of the system. I could certainly have done that. But it felt like that was quite a heavyweight way of doing this. So I cheated. So one of the things that I did was that I just gave it a prompt that told it something about how I'd like it to write the code. And so I said I'd prefer a more modular solution and a separation of concerns like this, and described what I wanted. And so it generated those. So I didn't do anything else. I haven't touched any of the code itself. So I ended up with this. So I ended up with this model that was broken out into 2 different modules in my solution. This is very, very simple code, I realize. But it worked. It passed all the tests. So my only inputs in programming, this exploration of a potential for the 5th generation programming style, was I gave it a canned description of what ATDD is that I've used for a variety of different projects now that I've been playing with. And I gave it the scenarios that I wanted it to meet. And I gave it a little architectural tip when I didn't like the code that it generated. Now, I'm not sure. I think I was chatting to a friend of mine yesterday, and he's an expert programmer. And one of the we were talking about this, and one of the things that he said was that he thinks that's where programming is going to go. It's going to be us specifying what we want to achieve with some degree of accuracy and precision, and giving it tips about how to make it more scalable, more resilient, the kind of architectural tweaks that we want to achieve. Now, we could do that through testing as well. The bit that makes me nervous about that is I don't know how that second part fits in very easily. The problem with that is I've been programming professionally for 40 odd years. And so I've got a fund of experience. I've screwed up in more ways than probably most people in the room. And so I've got lots of different rules of thumb in the back of my head that say, don't do that. And so when I look at some code that the AI has generated, I'm going to say, oh no, don't do that. Where do we get that if programmers aren't going through that? If the AIs are doing all the easy stuff, we're going to lose the ability to do that quite quickly, I think. The other problem is if the stuff of the AIs going and cheating in a variety of interesting ways is carried out further, then how long is it before we're not going to be able to read the code that the AIs generate and be able to look at the code and say, no, that's not right? There have already been demonstrated examples of AI inventing their own languages to talk to one another more efficiently. There have been examples of AIs cheating to shortcut results. There have been all sorts of things like this that suggest if you ask an AI to build a support girder for a bridge or something like that, it will build something that no human designer would think of, but it will be more efficient. But it's not something that we would intuitively understand. How long before they're doing that to the code that we're looking at? How long have we got? Well, we're still going to be able to interpret what's going on. These are deep problems, and I think that trying to find ways of exerting some more control over what we're doing is probably very important. There's another angle to this in terms of what this means for us all in terms of careers. And again, all of this is, I think there's some stuff in here that's true. I think there's some stuff in here that's probably not. I think there's some stuff that's a bit more speculative. So I'm not trying to say that I know all of the answers, because I certainly don't. But I do think the problems are true that I'm talking about. And I think this has some implications for where we go as a profession. I'm currently working on a video for my YouTube channel that there are 3 different kinds of programmers that I characterize as coders. So if you've ever said, I would have got it right, but the requirements were wrong, you're probably a coder. You're not really professionally solving other people's problems with software. You're just translating somebody else's solution into code. That's the easy part. Then there's software developers. Software developers are solving problems with software for people. And they're thinking in terms of design. They're thinking on a slightly different scale. And that's a different kind of skill and a much more valuable kind of skill. There are many fewer software developers than there are coders in the world. But I think that the coders are at risk because the AIs can do a better job of it than them. If we can give them a solution, they can do it faster and more quickly. Software development, I don't think that's going out of fashion very quickly, but software development takes some of the skills that I'm talking about. Then there's software engineers. My characterization of a software engineer at the level of a soundbite is if you can determine that your software works after every small change, then you're a software engineer. And if you can't do that, you're not there yet. And there are fewer of them than there are software developers. But that's a kind of progression in terms of value. And I think that's probably the order in which those people's jobs will get subsumed by AIs. It's going to be in that order, is my guess. Coders are going to go first, then software developers, then software engineers. I think that what we're talking about here is software engineering. And I think this is where humans add real value into the process. So, my conclusions. Natural language is simply not good enough. It's not a replacement from coding. And I think that the hype around just being able to talk to AIs and get it to generate all of the code is just that. It's an illusion. There's a much more value to our skills than only typing code. Our skills are fundamentally about problem solving and being able to decompose problems in a way that we can help to solve them and understand them in depth. And I think those are the skills that we should be focusing on, because those are the really high value skills. BDD style domain specific languages are a viable alternative to using human languages to more accurately, more precisely specify what we want to happen. And that's bringing in ideas that are familiar to us. They're ideas from domain-driven design. A DSL is a good implementation of a ubiquitous language for the problem domain in which we're working. And thinking in those sorts of terms, having those sorts of skills is important and valuable, I think. Automating testing from a solution is, to my mind, a joke. It's not real. And I'm getting adverts every day in my email for products that claim to do this, and I think it's unfair to call them scams, but they're not going to last. This is not going to be where the value lies. I think the skills to analyze and decompose problems is the real core of our professional discipline. This is what we are good at as a group of people. This is where we should focus. This is primary. It's not the typing of code. And I say, I'm going to miss that. I'm one of the people that when the AIs write all of the code, I will still be writing code sometimes just for my own entertainment, because I like writing code. Don't get me wrong. I'm not looking forward to this transition. I don't want to do away with writing code. Writing code is great fun. But that's what the assembler programmers said when high-level programming languages were invented. Who writes assembler professionally? There's a tiny, tiny percentage of people that do that these days. We need a different model for the role of AI in developing software, I think. And my proposal is AI assistance is a smart compiler. And if we treat it like that and use it like that, I think it helps us to think about these ideas in different ways. I know this is a very opinionated presentation. It's a new one that I made for you, talking through with Dave. This is the first time that I tried it out. I'm very interested to hear if people have any questions or any observations, very interested to hear them. But that's the end of my talk. Thank you.